students. How are you all? I welcome you all to today's class, and I'm your chemistry teacher, Chidera. Today we'll be looking at chemistry for SS2 students, and we are still looking at electrolysis. Now by the end of the lesson, the students should be able to state the two laws of electrolysis, write some calculations on electrolysis, and state and explain the uses of electrolysis. Now, I told us that we are still talking about electrolysis, and if you can remember from our last classes, we were talking about the meaning of electrolysis. We actually saw some certain terms of involved in electrolysis and all that. Now we say that electrolysis is simply the chemical decomposition of a compound brought about by the passage of direct current through that same compound, either in solution or in molten state. Now, we'll be looking at the laws of electrolysis. Remember, I told us also earlier that any product that is formed at electrolysis can be determined by three different things, according to Michael Faraday. Remember, he was the one that discovered electrolysis. And these factors are the position of the elements in the electrochemical series, the nature of the electrode, and the concentration of the electrolyte. Now, Michael Faraday also discovered that for the quantity or the amount of the products that can be formed or liberated at any of the electrodes, that three things can actually be involved. Number one part of it is the magnitude of steady current that is passed through the electrolytes. Also, the charge on the ion. This is hydrogen ion. The charge on the ion, and also the time taken for the particular current flow. And using these three main factors, he drafted out two main laws that are referred to as the Faraday's laws of electrolysis. Now, the first Faraday law of electrolysis states that the mass of an element discharged at the electrodes during electrolysis is directly proportional to the quantity of electricity passing through the electrolyte. Now, he had the electrolytic cell set up where he actually used a particular electrode, an electrolyte made of copper electrodes and copper tetraoxide 6 as the electrolyte. And he discovered that the mass of the element, maybe it's the mass of copper or mass of anything, that can be discharged at any of the electrodes during electrolysis is directly proportional to the quantity of electricity passing through that electrolyte. Of course, mathematically, from the whole equation, we can state that mass is directly proportional to the quantity of electricity. M directly proportional to Q. Now, in physics, we already have a particular knowledge of the fact that the quantity of electricity that is passed through a circuit, or for us, we call it the electrolytic cell, can be given as the product of currents, that's I, and the time taken, for the current. So definitely, automatically, you can still say that Q is equal to I times T, current times time. So from this, we can put up something to say that, so if we still come to the point that M, we said M is directly proportional to Q. So if we still say that M is directly proportional to IT, we still mean the same thing. Now, this is mass. Mass is measured in grams. Quantity of electricity is measured in coulomb. But at times, during some calculations, you might be given the values of current and time. Now, current is measured in amperes, while time is measured in seconds. So if you are given the value of the current and the time, you can easily determine the quantity of electricity passed. Now let's go back to the second law of electrolysis. We'll see that during our calculation. The second law of electrolysis states that when the same quantity of electricity is passed through different electrolytes, the relative number of moles of an element discharged are inversely proportional to the charges of the ions on the element. Now, Faraday actually had a setup of two different electrolytic cells, making use of copper and silver. Now, for the copper cell, we made use of copper electrodes and copper 2 trisulfate 6 as the electrolyte. Now, for the silver, he made use of silver electrodes, that's the anode and the cathode, and then silver nitrate. Silver nitrate, NO3. Now, he actually prepared a setup in series, and he discovered that if the same quantity of electricity is passed through the both cells, now at a particular time, and the time is steady for the both of them, he actually discovered that the number of moles of elements that will be discharged at any of the electrodes is inversely proportional to the charges of the ion. Now, in the sense that copper exists in copper 2+. This is the charge of copper. Remember, this charge shows that copper needs 2 electrons. Now, for silver, is this. Now, these are the charges on the 2 electrolytes, or the 2 ions that are actually formed. Now, according to Faraday, he discovered that with the connection in series, that the number of moles that this one will form will just be 1, whereas the number of moles that silver will form will be 2. Why? Because both of them are making use of the same quantity of electricity at the same time. This one will have to produce double of the charge of copper so it can meet up with it, whereas that of copper will produce just once on its own. It's only silver that will have to do the work of meeting up with the charge on the ion of copper. So with this, he actually made this discovery, and mathematically he said that the number of moles is inversely proportional to the what? To the charge. Inversely proportional, of course, to the charge. Now, with this also, he came to an understanding of the fact that 1 Faraday, he discovered that 1 Faraday, or rather the minimum amount or minimum quantity of electricity that can be required to liberate 1 mole of a singly charged element. When we talk about a singly charged element, we're talking about silver 1. This is just 1 charge. We talk about this. We can talk about potassium. So we just talk about the singly charged elements. Now we discovered that the minimum quantity of electricity that is passed through the electrolysis or the electrolyte of singly charged elements has a value of 96,500 coulombs. So according to Faraday, it will take nothing less than 96,500 coulombs as the quantity of electricity that will be required to discharge any singly charged element. Now, obviously, according to him, assuming we have something like carbon is doubly charged, has 2 ions on it. Definitely, it will take 2 Faradays to discharge this one. That is 2 times 96,500 coulombs. So, and they actually gave this value Faraday. So 1 Faraday automatically is equal to 96,500 coulombs. And obviously, 1 Faraday is equal to 1 mole of electron. So we understand more what Faraday was talking about in his laws of electrolysis. The first calculation we are going to be looking at today is calculate the mass of silver deposited when a current of 2.6 amperes is passed through a solution of a silver salt for 70 minutes. We have the value of silver to be 108, and 1 Faraday, as I told you earlier, according to Michael Faraday, is 96,500 coulombs. Now let's solve this. Now, from this question, we have some values. We are meant to calculate the mass. We are given a current, I, to be 2.6 amperes. It was passed through a particular time, so we have our time. as 70 minutes. Now let's look at these parameters. I know you've actually got the right. This is in amperes, but our time is in minutes. So obviously, and the normal SI unit for time should be in seconds. So we are going to be converting the 70 minutes into seconds. Remember, don't forget that 60 seconds make 1 minute. So obviously, 70 minutes will make how many seconds? Cross multiplication should give us 60 times 70 over 1 seconds. So with this value, we can definitely get the value of this. Now, we are giving our I, that's the current, and we have the time. So we can definitely determine the quantity of electricity that can be passed. Is equal to IT. So we have 2.6 times. Our Q, that's the quantity of electricity, is 2.6 times 60 times 70. So we have a simple value of 10,920 coulombs. Remember, coulomb for the quantity of electricity used. Now, we can't just make use of this value like this, IT. Of course, we have to remove this proportionality sign by, you already know, introducing the proportionality constant. So you have something like this, IT. So I would have said let's proceed by just fixing in the Q IT since we've got an IT and just get the mass. But this value is very important. Now how are we going to get that value? We'll get the value using this information that we have here. The fact that 1 Faraday is equal to 96,500 coulombs and that a silver atom is 108. Now let's solve. Don't forget this value. Right. So now there are things that you are meant to know whenever you want to have any calculation using Faraday's laws. The first of all is the equation of the reaction. Now we are told that silver was what was used in the reaction. So therefore our equation will be related to silver. Of course, this is 1 electron because of this is just 1. Will give us the silver atom. So this is the equation of the reaction. Now another thing that you should know is that 1 mole of electron is the same thing as 1 Faraday. Remember we said that 1 Faraday is the quantity of electricity, the minimum quantity of electricity that can neutralize or liberate or discharge 1 mole of electron. So we have 1 mole of electron here, definitely 1 Faraday. And also the number of moles of silver is 108. So from here, we can easily get our calculations. 1 mole of electron gave rise to 1 Faraday. 1 Faraday. So automatically, 1 mole is equal to 96,500 this. Now, if 1 mole was able to give us this, how many moles would this one give us? I hope you're understanding. How many moles with this value of the quantity of electricity, that's the new quantity that we have here, how many will it give us? We have 10,920. This. Definitely we have a cross multiplication sign. We have 96,500. Okay, let's go this way. 1 times 10,920 over 96,500. Now we have this. So let's hold this value for now. Remember that 1 mole of silver, 1 mole of silver is the same thing as 108. 108. So definitely, here that we have a value of 1 mole. If we still replace this one with 108, we will not be wrong. So automatically we have a value of 108. Remember we're talking about 1 mole of silver times 10,920 all over 96,500. 500. Now if you solve it very well, you will get a value of 12.22 grams. Now this will be value for gram. This one is in column, this one is in column. Cancelling it out, we have this just the value in gram, 1.22 gram. Now we've actually gotten the mass of silver that will be deposited at this particular current at this particular time. Now let's solve the second one. Number 2 question. And from number 2 question we have, by passing an electric current for 1 hour through a copper and silver calorimeter connected in series, 1.28 gram of copper was deposited at the cathode of the copper calorimeter. Calculate the strength of the current used. Now in this one, we are actually given the value of the time as 1 hour. We have the value of our mass as 1.28 gram. Okay, that is the only one. Okay, we are meant to look for our current. Now, definitely, we have work to do. Now, this time is an hour. We need to convert it to seconds. First of all, we already know the fact that 60 seconds make 1 minute. So we have that. Okay, and 1 hour definitely 60 minutes. So we have 60 times 60 divided by 1, which is automatically 60 times 60. 3,600 seconds for this one. Now, we're actually giving an information, and of course, the first thing to do is to write the equation of reaction. So we have copper 2 plus, gaining 2 electrons to give us copper atom. So unlike the first one that we solved, that just made use of 1 Faraday, this one is going to be represented as 2 Faraday because 2 electrons was actually added to the copper ion to give us 1 mole of copper. Now getting these informations will help us. 1 mole of copper was formed using 2 electrons or 2 Faradays. And we know that 1 mole of copper here is 63.5 and 1 Faraday is 96,500 coulombs. Now, if 1 mole of copper was formed using 2 Faradays, and of course 2 Faraday is 2 times 96,500, while 1 mole of copper is 63.5, of course, gram. So if 63.5 gram, 1 mole of copper, actually formed 2 Faradays, 2 times this. Now, how many? What's the quantity of electricity that will be formed using 1.28 gram? Remember, we are giving 1.28 gram. That is what we are going to be working on. We have it to cross multiply. We have 1.28 times 2 times 9,600 coding, so you don't get confused. You have this in gram. All over 1, okay, all over there, sorry, 63.5 gram. This gram can just have this, and we just have our columns here. Definitely we have a value that will give us 3,890. That if you divide this properly, you have this value. But this value that we just got here is for the quantity of electricity, whereas we are asked to get the value of current. Now, how can we actually get the value of current? Using this one that we have, we know that Q is equal to IT. The Q that we've gotten here is 3,890 current times the 3,600. Let me do it so you can see it. Q is equal to IT. Our Q is 3,890. We are looking for our current times the time 3,600. Now, to get our I, we just have to make our current, that's the I, the simple of formula. And so we have that. Of course, to make sure the formula, you divide by the coefficients. You divide by 3,600, 3,600. This will go out for this, so we have our I just below to give us 3,890 divided by 3,600. And the value that we get there will give us the value for the current, which is 1.08 amperes. Remember, amperes is for current. Now, try as much as possible to solve more questions on laws of electrolysis so you don't get confused. And I hope you don't actually get confused by the number of electrons and the number of moles, because they are the things that actually will determine your procedure for solving. I'll be looking at some of the uses of electrolysis. We have one to the extraction of metals. We have purification of metals, electroplating, and preparation of certain important compounds. Now, so many metals actually exist as ore. Now, we already know the fact that sodium chloride, sodium precisely, is actually a metal, and it exists as sodium chloride. That's the rock salt gotten from the sea. Now, how can we actually make our sodium to stand on its own? That's after extraction, we have to purify this particular compound to give us just the particular sodium that we need for any reaction that we want to go for. We can make use of electrolytic processes. Now, we have to take notes of the electrodes that we make use of and the electrolytes. So we won't have to make use of the electrolytes that will react and we will not get what we want again. Now, electroplating, this is simply the coating of a substance with another substance. Let me use this one, coating of a metal by another metal with another metal. Now, most of the iron plates that we actually see that they are being coated with some other metals. Now, most times, we also notice that the jewelries that we put on our wristwatch, when you buy it from the market, it will be very shiny, either silver or gold. But as time goes on, you find that it starts going off, it starts rusting, and gradually you find that it turns black, and you will now notice that it was actually made of iron. Most of them are actually electroplated using electrolysis and electrolytic processes. They simply bring the particular metal that they want to electroplate, make it the cathode, then get the silver or the gold and make it the anode. Then make use of the silver or the gold as the electrolyte. Now with that, they can easily coat another metal. They can easily coat a metal substance with silver or gold. So making use of electrolysis, we can go through electrolytic processes or electroplating, the coating of a metal by another metal. Now during electrolysis also so many other compounds and very important compounds that are used in the chemical reactions can actually be formed. Now in conclusion, we looked at the two Faraday's laws of electrolysis, and we saw some terms that of Faraday. We said that 1 Faraday is equal to 96,500 coulombs. We actually saw that from the Faraday's first law of electrolysis, that mass is directly proportional to the quantity of electricity, and the quantity of electricity can still be given as I times T, that's current in amperes, multiplied by the time in seconds. Now from the second law of electrolysis, it's actually revealed to us the more about Faraday and its value, and the fact that the number of moles formed is actually inversely proportional to the charge on the ion. Now we actually saw some calculations. Remember I told us there are things you need to note whenever you are calculating. At least first of all should be the equation of the reaction. The fact that 1 Faraday is actually the number of moles of electrons, or the number of moles of electrons, yes. Then don't also forget the value for every compound that or element that you're making use of. Now, you have your assignments here. Please and please, I want you to solve more questions. There are still so many other questions to solve on Faraday's laws of electrolysis, so you don't get confused. If you have any question, maybe because I was fast, you can ask me through my WhatsApp number. Now, for your assignments, I want you to solve these following questions. How many Faradays of electricity are required to liberate the following by electrolysis? A. 9 grams of aluminium. The value of aluminium is 27. That's the molar mass of aluminium. B. 4 grams of oxygen. The molar mass of oxygen is 16. Now, number 2, calculate the time required to deposit 1.6 grams of copper from copper 2 tetraoxide 6 solution by passing a current of 0.50 amperes through it. Now we have the value of copper to be 63.5. Make sure you write your assignment, and if you have any question, please ask me and submit to my WhatsApp number 090-799-61788. See you next time, and thank you.